Alright, so as we look to practice a little bit more with our second fundamental theorem of calculus, let's just remind ourselves of what we're dealing with, okay? The second fundamental theorem of calculus stated that if we've got the integral from a to x of f of t dt, what does that equal?
F of x.
That's going to equal, now is it a capital F or a regular F?
Capital.
It's a regular F. Okay? But a regular F is the same thing as capital F prime. Okay? So that both of those notations are used. We've seen both of those notations being used. Don't let it confuse you when they switch from lowercase f of x to capital F prime of x. All right? Now, I'm sorry, I forgot the derivative in here. Okay, so it's the derivative. Move this over a little bit here. The derivative of the integral from a to x of f of t dt is lowercase f of x, or the derivative of the antiderivative. Okay? So the notation here we got to be a little bit careful with. All right, so as we're thinking about this, we need to make sure that we're careful. If I'm trying to find f prime of x on example 1 here, that means I'm taking the derivative with respect to x of the integral from -1 to x of the square root of t squared plus 1 dt. Okay? And we could then say that equals what?
Square plus 1 square root.
X squared plus 1 in the square root. Now, we should be careful here because what was the one condition for this?
If x, that's nothing, I think.
There was one condition. The function had to be continuous on the interval from a to whatever x you're working with. So, is it continuous? Is it defined at x equals or at t equals -1? Yes. All right. It equals 0, but that's the endpoint. All right. It equals 0, but that's okay. So it does apply here. It is going to be continuous. We know that as we move to the right, it's still going to be defined from -1 to 0 to 1 to so on for the all real numbers greater than -1. And in fact, this one, because t is squared, it's actually defined for all the values that are less than -1 as well. So the domain of the function here is all real numbers. Okay? Therefore, I know it's going to be continuous as well. So it does apply. Okay? All right. Now, this says, use the fundamental theorem of calculus to rewrite f as a standard function. Okay? So, now notice this doesn't go from pi over 2 to x. It goes from pi over 2 to x cubed. Now that's interesting. We haven't done one of these yet. Okay? So if I take f prime of x and I call that say that is the derivative of the integral from pi over 2 to x cubed of cosine of t dt. Okay. Let's see what happens. Okay, what do you think this would equal? Cosine of x cubed. All right? So that's what we think based on our second fundamental theorem of calculus. Let's try to confirm this using the same method that we did with the other ones that we started with, okay? Let's actually do the integral from pi over 2 to x cubed of cosine of t dt. Okay? So here we're wanting to see if we can confirm this. Yeah, this should be x cubed. So the question really that we're trying to confirm here is whatever that is up on the top, do we just plug it in? Or is there something else that we need to do here? Okay? Well, let's think. What's the integral of cosine of t dt? Sine of t. All right? So I need to evaluate that from pi over 2 or from x cubed to pi over 2. And notice here I'm finding what f of x, capital F of x is. All right? Well, that is sine of x cubed minus sine of pi over 2. What's sine of pi over 2 equal? 1. So I have sine of x cubed minus 1. All right, now, it said we want to find f prime of that, because if we're going to rewrite f as a standard function of x, f of x is going to be the derivative of capital F of x, right? Well, what's the derivative of sine of x cubed minus 1?
Cosine of x cubed times 3x squared.
Yeah, times 3x squared.
Okay.
Why it is this answer?
This chain.
Yeah, we were using the chain rule here. The x cubed is inside the sine, so we do the derivative of the outside. Derivative of sine is cosine. And then times the derivative of the inside, so it's times 3x squared. And then the minus 1 just becomes a 0, right? Because we're taking the derivative. Okay, so can we just plug in the x cubed? No. Okay? What are we going to need to do? Kinda. All right?
Change it up.
So this ended up not working exactly the way we thought it was going to work. Okay?
I didn't understand.
But that's because, notice, we're taking the derivative with respect to x, but now we're dealing with an x cubed. Okay? So it is kind of the chain rule idea. We would need to then multiply by the derivative of what's up there. Okay?
I didn't understand why.
Here we're taking the derivative with respect to x, but we aren't using just an x, we're using an x cubed. All right. So we have that chain rule idea going on. When we do the derivative, we need to consider the derivative of that. So it's not just a cosine of x cubed, it's cosine of x cubed times the derivative of x cubed.
Okay.
And that's what we showed there. Okay? So we have to be careful with that. Now that we know it's not that hard to do, but we do have to be careful with that. All right? So if I were doing this one, find the derivative of capital F of x. So I want f prime of x for this. So the derivative with respect to x of the integral from pi over 2 to x cubed of cosine of t dt. We just did sine. Or no, we did cosine. Okay. Now that we know the rule, though, we don't have to do the whole, what's it called? First fundamental theorem of calculus with the definite integral. Now we can rewrite it as cosine of x cubed, but times 3x squared. Okay? So the idea here is we can generalize this, all right? If capital F of x is the integral from a to some function, let's call it g of x, of f of t dt, okay, then f prime is going to equal f of x times what?
Derivative.
That's right, the derivative, g prime of x. Okay? And actually, it wouldn't be f of x, it would be f of g of x. Okay? So you plug this in instead of the t, and then you multiply by the derivative of it. And that's what we saw here. You plug the x cubed in for the t, but then you multiply by the derivative of x cubed.
Okay.
All right, so let's look at this one more example here. We're going to consider a particle moving along the x-axis where x of t is the position of the particle at time t, x prime of t is its velocity, and the integral from a to b of x prime, the absolute value of x prime of t, dt, is the distance the particle travels in the interval of time. Now, notice here, when we're talking about distance, that's different than what x typically gives us. X typically gives us the displacement. In other words, how far away from zero we are. Okay? If I don't care where I am in relation to the start, I just care about how far I actually moved, there are a couple of ways that we could handle that. All right? But notice here we have this absolute value that forces all of our directions to be positive. Okay? So we want to make sure we understand what we're talking about here, and that's why it's important to understand the original function as well. This is x of t is our position or displacement, how far from 0 are we? Okay, well, that's not what we're looking for here. We're looking for how far have we actually traveled, okay? So, it says find the total distance the particle travels in 5 units of time. So it says set it up as the sum of definite integrals, evaluate, and then check the answers in your calculator. All right, so we need to do a little bit of work here because we need the absolute value of the derivative of x of t. So what's the first thing we're going to have to do? Find the derivative, okay? So x prime of t, what are we going to have to use to find the derivative here? Product and chain rule. Okay, so
Oh my god,
the first one has a derivative of 1 times t minus 3 squared plus the first one, t minus 1, times the derivative of the second. What's the derivative of the second?
2 times t minus 3.
times 1.
Yeah, t minus 3 is to the first, times 1 is the derivative of the inside, so they were a little nice to you. Okay? And by the way, this is a good example where simplifying is helpful. Okay, so I'm going to factor out a t minus 3. And I have a t minus 3 plus 2 times t minus 1, so 2t minus 2 left over. So I know x prime of t is t minus 3, 3t minus 5. So now I actually have my derivative function.
Should multiply anymore, like to the t and the minus 3 into the 3t minus 5 at all?
I'm sorry, what?
Should we multiply those together at all or not?
Let's not, actually. We could for later on when we go to do the integral, but for right now it'll actually be helpful because one of the things that we need to do is we need to find the integral of the absolute value of that t minus 3 times 3t minus 5. Now, what's the a and the b here? 0 and 5. They said go from times 0 to 5. Okay? Now, why is it helpful in this absolute value to leave it factored initially? Find the zeros, okay? Because we have to find which part of this is negative so we can force it to be positive. All right? Now, it's nice, this one's a quadratic.
But they said total distance, not displacement.
That's true. That's why we found the velocity. X prime of t is our velocity. So if we find the sum of all of the velocities, that will give us the total distance traveled.
But total distance traveled is how much you moved, or is this the displacement?
It's how much you moved.
Oh, the total distance.
Yeah, total distance.
I had the mistake.
Okay? So we have zeros here at 3 and at 5/3. So right here, is this quadratic opening up or down? It's going up, so it's going to look like this, right? And that's important because as I do the integral from 0 to 5, this part here is positive. This part here is already positive. So I can do the integral from 0 to 5/3 of that just as it's written. And just for sake of writing, I'm just going to put the x prime of t here. And I can do also the integral from 3 to 5 of that x prime of t. Okay? But what do I have to do with that middle part? I got to subtract it. Okay? Because it's a negative area, and this says I want the absolute value. Guys, that's the difference between getting your final position, your displacement, and getting total distance traveled. Okay? Is forcing this part to be positive. So, by subtracting the integral from 5/3 to 3, that's going to make it so that I have a total distance. Okay? Does that make sense?
Oh, it's because the area of the velocity graph is the distance.
Yes. The area under the velocity graph is the distance.
So you get the integral.
Yeah. Okay? Now, here's here at this point, Alec, is where it might be helpful to go ahead and FOIL those together because we got to take integrals.
Okay, gotcha.
Okay? So, yeah, let's go ahead and let me change colors. I'll do this
So
in green.
when you were talking about zeros, it was helpful to keep them apart, but now we're trying to integrate together.
Exactly. Finding zeros, it's helpful to have it factored. But now, let's make this a 3t squared minus 9 minus 5, so minus 14t plus 15. That's what I'm taking the integral of. Okay? So the integral of that, what's the integral of
T cubed minus should have written
7t squared plus 15t. Okay? So, yeah, when I integrate this with respect to t, 3t cubed over 3 minus 14t squared over 2 plus 15t. That's what we're doing here. Okay? So now, I've got 3 of these. I've got to evaluate one of them from 0 to 5/3. I've got to subtract one of them evaluated from 5/3 to 3. So from 5/3 to 3, and notice I'm subtracting that one. And then I've got to add in that evaluated from 3 to 5. Okay? Now it's just a matter of a bunch of algebra. So let's go ahead and figure those out. Alright, so if we use the table on our calculator, we figure out the different values that we need, because I evaluated these at 5/3, 0, 3, and 5, because those are the only ones we actually need. So we need it evaluated at 5/3, so 10.185. Minus this evaluated at 0 is 0. So that's the first one. Then minus this evaluated at 3 is 9. Minus this evaluated at 5/3, which is 10.185. Notice it makes sense that that middle one was 0, or was negative. That's the whole reason why we're having to subtract it, is to make it be positive. Okay? And then we're going to add to it, this evaluated at 5 is 25, minus this evaluated at 3, which is 9. Okay? So, we have 10.185 plus 1.185 plus 16. So we have 27.37. Okay? And that is the total distance that this object traveled. Notice we did not end up 27.37 units away from where we started, but that's the total distance that we traveled in those first 5 units of time.
If you had the graph for the position, you got the graph line and you stretched it, you were able to get the value?
If we had its position and we stretched it,
Like the graph of the position, you got the line, just measured the line.
well, what we would have to do in that case, we would have to figure out the turning points. So we'd have to figure out critical values. Then we'd have to figure out its position at those different critical points. Okay? And at the end point. So if we were starting at 0, then if we found the first turning point was at 5/3, we'd say, okay, what was our displacement at 5/3? Then we would figure out, okay, where was our next turning point? Well, it was after 3 seconds. So what was our displacement there? And we would have to use that to calculate the distance. Okay? So we'd say, okay, where were we at this time? Where were we at this time? Okay, so we traveled this distance. And then we'd figure out where we were at 5 seconds and calculate that distance. So, and then we'd have to add the 3 distances together. If you think about what I just said, notice we're calculating 3 different distances and adding them together. So we're doing the same thing, just with a little more analytical as opposed to having to visualize it and figure out all turning points and all that kind of thing.
If you had like the graph in the form of a string, you got the string in there, would it give you the distance?
Only if when you did it with the string, you folded it back on itself when it changed directions, and then folded it back on itself when it changed. So that little part in the middle would actually be covered by 3 strings, where it had come back and then turned around again. So, yeah.